Hello, welcome to a walkthrough of the Edexcel GCSE Paper 2 sample paper. So this is a 2 hours long paper, so slightly longer than the first one, which is more theoretical based. The first paper covers all the stuff from the specification. It is more theoretical. This is a more application based question, hence the name. So it's a slightly different style of paper, as we'll see. You can see we've got also a booklet containing pseudo commands. This is also the same as, it's also in for paper 1 as well, so this will just be an additional booklet that's on your table in your exam. In fact, let me try and show you it. So it's just, as I say, another booklet which you get, and it's got things like, basically it's a reference you can use for algorithm questions and understanding what they're telling you. You don't have to follow this exactly, but this is explaining what their pseudocode means. Obviously pseudocode by nature is very relaxed, but this may be useful in the operators and so on. So that's also part of what you get given, and it is worth 80 marks like paper 1, I believe, so that's the same, but you get a bit more time because it's this more application based paper. In fact, one more thing, you can't use a calculator, so that's quite important, so don't bring one into the exam. There's a whole set of videos that cover both paper 1 and paper 2. There's 2 playlists on my channel that cover all the theory needed. As I say, there's less theory needed for this. In fact, they could ask you about anything in paper 1, so that's a slight issue, but if you've revised paper 1 thoroughly, then you should remember it for the next week, whenever this paper would be. So to begin then, all questions are based on a scenario, which is the difference for this paper. So this scenario is about Sparky Autos, which is a family-run business based on a farm. They offer visitors the opportunity to drive small electric cars around a racetrack. There are up to 20 electric cars available each time for a race. Each has a tag, so its number and position can be tracked using sensors, and it's got a number painted on its side. So this is information we're probably going to need as we go through. Firstly, when cars are serviced regularly to check they're safe and reliable, a service can be triggered by the car being run for 100 hours or if 30 days have passed. So 2 variables that need to be created to store data for each car. We can use what we've been told here. We've been told that it's been run for 100 hours, so running time of car perhaps, and this would probably be in hours. And also perhaps the time or probably the date of the last service, so date, because you'd use that to calculate how long has passed since it. So there are 2 examples. Also, I guess you've told us that it's got a number and position, that would be 2 other variables. So there's lots of examples here that could work for this scenario. And each car takes at least 30 minutes to service. Older cars take longer to service. 10 minutes is added for each full year of the car's age. So the year of purchase is known, so that's going to be another variable. And we're going to construct a general expression showing the time you need to service any car. By general expression, it just means like just algebraic expression. It's not like a Boolean expression or anything like that, it's just a normal expression. So it's only 2 marks. So to work out the car's age, we know the year of purchase. We need to do basically, so it's going to be current year minus purchase year. I was doing my variables in camel case, which is where you do the first letter of the first word lowercase and the first letter of the second word uppercase. That's just my preference. So that's going to be part of our equation. So that's it's the other bit we need to work out. So each car takes its 30 minutes to service, so it's going to be just at a base 30 minutes at a minimum. So if a car's brand new, it's going to take 30 minutes generally, plus 10 minutes times this. So we need to do, so maybe let's include this, so we can get rid of this now, and that would be our actual equation. So hopefully you can see what this means. It's going to be 30 minutes just generally at a minimum, but also 10 minutes times the age of the car. So the older the car is, the longer it's going to take by a factor of 10. So that's what this is saying. And a program can be used to determine information about the cars and the drivers. Complete the table to show an input, a process and an output using the following information. So each race has got 5 laps and there are 10 cars in the race. So 3 stages then. So we need to work backwards here. So the process in the first one is to calculate overall total time for any car in the race, and the output is going to be the sum of lap time. So basically this is saying that you've got a lap time for lap 1, lap 2, lap 3 up to lap 5, and then it's going to add these together and produce the sum. So what we need to input is the 5 lap times per car, so lap times, and it's going to be for each individual car. It's adding them up by it's adding them up, and then it will give you the sum of the total lap times. And for the second one, the process bit is missing, so 10 car numbers and 10 total times are inputted. So that makes sense, there are 10 cars in the race, and then the output is going to be the car number with the quickest total time. Well, this is just going to be to process is going to be to find the car in first place, or to find the winner. because we're returning the car number the quickest total time, this is going to be the winner because they've got the quickest time. And then the output is missing for the last one, so the input is 10 car numbers with 5 lap times each. Find car with quickest lap time. Well, this is going to be, the output is going to be the car with the quickest lap time. So obviously you could not win the race and still get the quickest lap time as an individual lap because there are 5 laps in total. So that makes sense. Find car with quickest lap time. What it's going to be, it's going to return the car with the quickest lap time. That's, I think, the most obvious one. There's just a bit of deduction here based on this scenario. And then the arithmetic operator modulus manipulates numbers. It could be used in the calculation required by the processes above. The purpose of the mod function. So mod is okay, so it's best just to explain what it does. So mod returns the remainder from a division. So for example, I don't know, 12 mod 5 would return 2 because 5 goes into 12 2 times, remainder 2. So that's where we get 2 from because it's, as I say, returning the remainder. Another example, if we did, let's say, 20 mod 2, well, this is going to be remainder 0 because this is going to return 0 because 2 goes into 20 10 times, remainder 0. So that's not going to return a value for that. A different one, if it was a different question, of course, would be div returns the integer part. So it would return 2 here and return 10 here as opposed to the remainder. So it gets rid of remainder, but that's obviously a different operator. And this company gives discounts based on the number of visitors in a group, and the pseudocode for an algorithm that determines the discounts is shown here. And we need to, for this, complete the table to show the output of this algorithm based on the given input. So 3 lots of inputs here, 3 pairs of inputs, and we just got to trace through this algorithm to find the output. So it should be relatively straightforward if you concentrate. So first of all, we've got number of adults here as 8. So if number of adults is greater than 1, well, this is true because 8 is greater than 1, so we can just do 1 here because we've got an AND operator here. Number of children is greater than 0, well, it's not, this is going to be 0, so this will in total return to 0 because AND has got to have both sides to be true, so this won't get executed. It'll go to else here, so we can move on. So if number of adults is greater than or equal to 10, well, it's not, so we go back to else here, we skip this if statement. It is greater than 5 though, greater than or equal to 5, so we send a small group discount to display. Next, we have to get rid of this little working, and the next one with 2 and 2. So it is greater than 1, so that is 1, and number of children. So this is now true. So it's just going to return this, so it's going to be family discount this time. And then finally, 12 and 0, it's going to be, again, this is not going to get executed because this is going to be 0, so we'll skip to else, with a main else here. Then nested, we have number of adults is greater than or equal to 10, well it is, so this is just going to be large group discount. So it should be relatively self-explanatory, I suppose. This send to display is their same way of doing printing, that's just their pseudocode and representation of that. And also, obviously, this is greater than or equal to, so if this was greater than or equal to 0, then the first one wouldn't have turned out how it did because 0 it would value to true if this was greater than or equal to, but it's not obviously, so that it's not really relevant. But this is just a test of how you can trace through an algorithm. Now we need to construct test data to meet the requirements set out in this table. So the 2 requirements being that we have a condition generating regular pricing and the smallest group qualifying for family discount. So let's do the first one first, surprisingly. So we're already told that it's going to be 0 for number of children. So what data? And it won't just be one bit of data, perhaps it could be multiple bits of data. So generating regular pricing. So how would regular pricing get executed basically with 0? Well, if it has got 0, then as we saw before, it's going to skip this first bit, so that's fine. So if number of adults is greater than or equal to 5, then this. So basically we want to work backwards because we don't want this to get executed, we don't want this, we want this. So we need to work out how that's going to get executed. So greater than or equal to 5 is going to do this. So less than 5 is going to be this, which is what we want. So it's going to be 1, 2, 3, 4 as our inputs. So it's going to be any of those 4 would produce this condition. And then for the smallest group qualifying for a family discount, so that's now, let's get rid of some of this working. So family discount is going to be up here. So we want this. So the smallest group that qualifies for this, well, number of adults has got to be greater than 1, so i.e. it's going to be 2. And number of children has got to be greater than 0, so it's got to be 1 for both of this to be true, and then it will execute this. So it's going to be just 2 and 1, that's a slightly simpler one, I think. So just to be clear, because this is a slightly different question to what you'd perhaps expect for this topic, it's just asking you to produce some data that would return these conditions. And for a 2 marker, we've got to say 2 techniques the programmer could use to make the code easier to read. So about improving readability, how easily it could be understood. Well, this is just states, so very simple. So comments are always a great one to talk about. Your teacher would always get you to do comments, I'm sure, which are really useful for explaining your code. And also things like indentation. So if we go up, we can see indentation is just where you add gaps in between the start of a line. You could stack this up as just it's all written like this, but it makes it harder to see what belongs to what. You can see very clearly here that these are nested within this else statement, but if they weren't, you couldn't really know when it starts and begins, so it makes it a lot easier to read. This is much easier to understand what's going on. Another one you can talk about is descriptive identifiers with things like variables, subroutines, and so on, as in instead of just saying from random, so here we've got dates, we've got extra visitors, it's quite clear what that means. They could have chosen a completely random name, but that wouldn't be very helpful. So actually looking at this then, some more pseudocode, and in the sum of it, open for more hours each day, and that means additional members of staff are needed, and the pseudocode works out the number of days that additional members of staff are needed is shown. So we need to complete the table to identify the line numbers that show one example of each of the following constructs. Okay, so first of all, a comment is often, so this is a comment, is often signified with a hash, and yes, so that's line number 2. And then an integer variable initialization, so we have, so these are all arrays, because you've got double brackets and you can actually see the data there. So set length to length extra, so length is going to be an integer, so that's going to be 9. You could also say 10 or 11 as well. And selection is where you make a decision, a binary decision, so that's an if statement basically, so that's going to be 14. In fact, because it says line numbers, we have to do, it's going to be 14 to 16. If we didn't do that, we'd probably lose a mark. And then iteration is where you actually repeat, so this is 13 to 18. It's a good example of a construct being nested within another construct. Now we have a trace table question. We have to complete the trace table for the code, which I've copied in here. And trace tables are relatively straightforward. People often get stressed about them because they assume you have to fill in all the boxes. You really don't. It's very relaxed. They're meant to be for testing, so they're meant to be useful to you as a programmer. So they're really not worth getting too worried about, to be honest. The gaps you leave actually aren't that important. It's if you basically want to be able to look back after you've finished it and understand what's going on, or you want an examiner to do it more relevantly. So first of all, we've got 4 variables we're keeping track of here: length, count, index, and the array extra being indexed by index variable. I don't know why this is curly braces or brackets, sorry. It's square brackets here. That's obviously a mistake by the exam board. So first of all, we've got 4 initialization lines here. They're not relevant to us here because we haven't got them as columns. We're indexing extra, but we're not worried about it at the moment. Yeah, so we can ignore that for now. So first of all, the length is set to the length of extra. So extra's got 3 items in, so this is going to be 3. Count can be set to 0, and index can be set to 0 as well. You could do like this if you wanted to, instead of writing those 2 in, but I think that's unnecessary. As in, you could go on to the next line because they're on separate lines, but you're kind of doing one step here, just assigning a value to them, so it's really not a big deal to go on separate lines, but you could do it if you really wanted to. So now we have a loop here, and this is an interesting loop because the condition is after the main body, which you don't often see, so that means we have to execute this at least once before checking the condition. So that's just a special type of loop. So first of all, if the index of extra, which is now, so extra with an index of 0, the 0th item in extra is y, so we can write that down on a separate line because it's a different kind of construct. So it is true, so that is true. We can set the count to count plus 1, so count now becomes 1, and then set index to index plus 1, so this becomes 1 as well. And now we can check the condition. So does the index equal the length? Well, it doesn't. 3 is different to 1, so we loop again. We evaluate this bit again, so now, oh, that's not good. Now the index is 1, so the first item in this is n because we're starting counting from 0, so we write down n again, but this now doesn't execute because the if statement condition hasn't been met because it's not y, so we skip this step and we set the index to index plus 1, so we don't do anything with count at the moment, so this becomes 2. Now does the index equal the length? Well, no, it doesn't, so we go back. Now extra index is extra, so the second item is y again, So this does execute, so this count is set to count plus 1, so it's 1 at the moment, so it now becomes 2, and index now becomes 3. And now this condition is met, length does equal index, so this is it, we've run out of code, so we're finished. So clearly as I've gone through that, I've made some choices about where I'm actually putting my gaps. It doesn't hugely matter, it's got to be in order, so basically if you collapsed these columns, it's got to be in order. But other than that, it's not hugely important. I mean, you'd have to align them up properly and so on. Basically, as I say, you've got to be able to look back and understand what's going on, and you'll get the marks. And trace tables are used in order to check for logic errors. So for example, clearly length and index are meant to converge here because it's meant to be going through the loop. But for some reason, say if this jumped to 4, you'd be able to see exactly what step it happened in, and then you could change your code so it makes the process correct. On the subject of errors, we've got an error because I've written tes instead of set. So what type of error is this? Well, this is a syntax error. Syntax is sort of the rules of a language, i.e. that in this pseudocode, set is for a variable, so that doesn't make sense. But anyway, set's for a variable. Tes isn't actually an instruction in this pseudo language, so that means you've broken the syntax by making that mistake. So it's a syntax error, and we've got to explain it. So we can say because tes is not part of the language's rules, i.e. by using it you've broken the rules. Now we've got more pseudocode, and this is for an algorithm that determines the maximum number of visitors in a 3-day period. And lines 10 and 13 have a logic error each, and we have to identify the error in each line and construct new lines of code that will correct the errors. Not given a lot of space here, so presumably it's quite a small change. So logic error, I should have really said, is where you expect code to do something and it doesn't do what you expect it to, even if it does run. So if the rules haven't been broken, it's not a syntax error, but it's not working exactly how you expect. So line 10, first of all, is where we're setting maximum to 100. So let's see what the code's doing. We're looping through the visitors array, and if that item at that point is larger than the current maximum, then it's updated, i.e. this variable is meant to keep track of the current maximum in this array, and then it's outputted to display. So basically the issue is, I don't know why it's set at 100. So 100, there's no reason for it to be set at 100. Basically this would work because 122 would update this, so would 147. But say this was in the middle of winter, no one was coming to this race car track, and if these were all lower than 100, then you're not going to get any value. It's not going to make sense because you're going to get 100 back out, which is what you want. So this may as well be set to 0. There's no reason for it to be set to 100 basically. That makes no sense. You may as well set it to 0 or, well, yeah, 0 or any negative number. So so the error is that maximum is set too high. You're comparing it to kind of an artificially high number for no good reason. So the correction would be to set it to 0. I mean, 0 would work, and 0 would work with all combinations. If one person turned up in the 3 days, that is still going to be the maximum. It doesn't make sense otherwise. As I say, you'd get 100 out even if these were lower, so that doesn't make any sense. So okay, that's relatively straightforward. And line 13 is this for loop. So for index from 0 to the length, so the length is the length of visitors, so this is 3. Okay, so the issue here is that we're basically going out of bounds. So we start off with 0, which is fine with 0 indexing. So we start off with the first one here. This goes to 1, this goes to 2, then it goes to 3, because length is going to be set to 3 in this example, and there's no item in the third index because we're going 0, 1, 2, 3. So basically we're going out of bounds. So the error is array indexed out of bounds, which can be a fatal error. And so to correct it, you want to go from 0 to length minus 1, because we're counting from 0. If we weren't counting from 0, this would be from 1 to length, but otherwise we have to do length minus 1. Now we need to complete this table to give the appropriate data type of a variable to store each of these items. So data type influences roughly what the data is, whether it's a true or false value or a word, but also influences how much space we've got. So we need to consider that as well. So gender of individual staff member, this could be a string, clearly could be male or female, but as I say, a character is a single unit of a string, but a character is only going to take up maybe 8 bits in memory, whereas a string is going to take up maybe a few bytes just by default. So this is a much better, so character is what you'd write here. Boolean, true or false doesn't really make sense for gender. You probably could, character is the most suitable, most appropriate for this because it's the smallest representation. You're taking up least the less amount of memory. So next one, whether an individual car is still under the manufacturer's warranty. This is for Boolean, i.e. it's either not or it is, so true or false for this condition. For mean number of hours needed to recharge the battery in a car, well, mean is going to end up with a fractional value, i.e. 2.45 hours. So this is best to be a real or a float, you could also call it. So this is where you get a fractional value. An integer wouldn't really work because you're doing an average here, it's meant to be accurate. And then the number on the individual car, this would be an integer because you're not going to have number 2.5 on a car, it's going to be discrete values, which is what an integer is, a whole number. Now each member of staff has a 4-digit ID number. They work a whole number of hours on the days they work, and they work no more than 12 hours in a single day. And it's open 7 days a week. So we need to draw a diagram of a data structure that shows the hours worked for each day of the week, include data for at least 2 members of staff. Slightly strange question. This is sort of totally application based. There's no theory that kind of explains this other than just what a data structure is. It's just a collection of data items that are somehow related. So it's asking for a diagram, so no code here, just basically it's looking for a table. We're looking for 2 rows, and we've got these fields here. In terms of, it's going to be the days and also ID number, so ID number plus days as our columns, and then 2 rows like that. So first of all, we've got the ID. Because we need to do at least 2 rows, we need to kind of just make up a staff member, so we can use this, but let's do the columns first. So ID, and it's going to be, it's 2 days of a week, so we can do, it doesn't actually matter, so it doesn't really matter what we call the columns basically, because in data structure, unless it's like a dictionary, you're not going to actually label the columns for fields. You're going to index them like we did before with an actual number, as opposed to, so this would be field 0, this would be field 1, 2, 3, and so on. So this is just defining the structure of what this is, which is going to be a 2D array because we've got multiple rows. So first of all, let's just use the IDs up there. So 3865 and 4722, so 2 separate members of staff. And then we can just make up numbers for the rest of it. So what is it? So they work on number of hours on the days they work. They work no more than 12 hours in a single day. So we've got to make sure they're not greater than 12. So this could be he or she is not working today. They're working 5 hours. 4, 1, 0, 6. So somewhat random data, but all I've done is made sure it's a whole number, as it says here, and it's not greater than 12. So this is kind of our data structure. This is our 2D array, so an array within an array. And really, so this, as I say, is just for structure, for names, and really I should have probably put Monday, Tuesday, and so on. This would have been index 0 if I'd done it properly. But that's less relevant, to be honest. It's more the actual data structure here. And how this is represented in a programming language is not really relevant to this question. It would just be a 2D array, basically, but you could do it in other ways if you wanted to. But this is, yeah, that'd be our 3 marks. Next question, when a programmer has written subprograms to help him in his work and pseudocode for a function to determine the amount of time elapsed between the car switch being turned on and turned off is shown. Okay, and the underlined item in line 18 has a name when used with a return keyword. State this name. Well, this is the return value, because you're returning a value to the calling routine, so it's the return value. Yeah, slightly strange question because it's sort of in the name, but there you are. It's also just a result from the function. And explain why the variable in line 2 total time is not reset when the pseudocode on line 16 is executed. So line 2 is here and line 16 is here. So set total time to time off minus time on. Normally this would reset this in the sense that this would change the value up here, but you can see we've actually, it's been declared here again. And this is all about scope. So this has global scope, this is accessible from all the code, but this is only accessible from within, this is local scope, within this function. So basically re-declaring it here means that this is a separate entity to up here. If the program treats this as a separate variable, you could specify this one manually, But unless you actually say that you want to access the global variable, you're going to access this local variable instead. So it's actually changing and resetting this local variable as opposed to the variable on line 2, even if they do have the same name. So to explain this without loads of arrows, we can say that variable on line 2 is global, whereas on line 16 it is local. So only the local variable changes. So the terminology is that it's local to that function here. So it's not accessible outside this function, which is why we have a return value, because we want to pass some data out that isn't normally going to be accessible. And now I need to explain the effect of executing the pseudocode on line 17 this time, which is, I've covered it up, but it's this one here. So set total time to total time. Well, total time is in caps here, which is going to tell us that it's a constant. So just by convention, usually uppercase variables are constants, and this is going to confirm that for us, the fact we've actually declared it as a constant. So that means a variable can change. Clearly we're updating it and we're doing all sorts of stuff, but a constant is similar to a variable. They hold some data, but they can't change. So once you set it for the first time here, it's not going to change from 10.25. So this is why this has this will have no effect basically, because it's just not going to let you change for constant. So total time is a constant, so the value cannot be changed, hence line 17 has no effect. So line 17 it's not going to work. Basically that code's going to be wasted. And validation is required for the items underlined in line 13. Construct 2 validation tests, and for each test give a piece of invalid test data for 4 marks. So quite generous. So what line was it? Was it 13? Okay. So 13 is here. So it's been underlined. So time on and time off. What do we need to check here? So a validation test is there to make sure data is within the correct range or of a certain length and so on, to basically make sure it's not going to cause issues by being invalid. So we've got time on and time off. We're not actually told exactly what they are, but we can assume they're a time variable, i.e. they're the time at this the time they turn on, time they turned off, as in 3 o'clock, 4 o'clock. I mean, you're subtracting it to work out the total time elapsed in between. So that makes sense. So basically you need to make sure these aren't negative for some reason. So they can't be negative because that's going to cause mayhem. That's not going to make any sense. So the validation check we can do on both is to make sure that they are, so time on is greater than or equal to 0, and so is time off. I need to give just a piece of invalid test data for this. So invalid for this could be -5, -3 even, and this could be -5. So just 2 ones that would fail this test. And this could be a bit of code we've just added in to make sure that the parameters passed in are valid and aren't going to cause any issues. Another one we could do, you can see we've got time off minus time on. Well, this time off needs to be larger than time on. So we could do another condition which is saying, is time off larger than time on? That makes sense. And we could just add a bit of data in the case where if it's not valid, then time on is larger than time off, which doesn't make sense. So that is another one we could do. Basically, you want to be thinking about what condition could we put in to protect our program, and then what data would invalidate that condition. I'm a pseudocode for a procedure that repeatedly checks for time as shown. The effect of calling this procedure is that the calling code waits for 5 seconds. So it's a wait procedure, and in this case it's hard coded to wait for 5 seconds. And we're going to amend it so that it waits for any number of required seconds without user input. So without user input means we're not going to have an input statement. Clearly it's actually going to get passed in with a parameter, so that's the amendment we need to make. As I said, at the moment it's hard coded for 5 seconds. We want to amend this so that it can work for any amount of seconds. So really the only difference is, I hope we don't have to copy this all out again. I think you possibly would, but I'm not going to. So I think you probably should copy it out in an exam. So the parameter is going to be something like int seconds, and then this is going to get replaced with seconds, because the data getting passed in is going to replace that. So you should probably copy this out, but that saves a bit of time. So it says without any user input, the way it'd be called would be wait, and then you supply the data. So say it was 10 seconds this time. Now you actually have flexibility. It's going to wait 10 seconds as opposed to just for... So instead you'd have to do wait times 2 in order to get the effect before adding this flexibility. At the start of a race, cars are placed on a starting grid in a staggered pattern. And when a car makes a false start, it breaks a light beam, and this notifies the computer system the race must be stopped if a car makes a false start. There's a maximum of 20 cars in a race, and a program is chosen to use a 1D array to store this data. So 1D array being just lots of data items stored as just a single row, as opposed to a 2D array, which is where you've got several rows. Okay, so assess how appropriate a 1D array is as opposed to using separate variables when storing this data for 5 marks. So we really want 5 points here. So assess means we've actually got to come to a conclusion at the end of our answer, but we need, so that would be a mark, we also need 4 points. So the answer is going to be that this is more appropriate than using separate variables, because if we've got an array with 20 cars in, we've got 20 items under one name, the array, otherwise we need 20 variables to keep track of. So this is all about flexibility really. So for example, if a company's name changed for some reason, as a program you don't really want to have to go through and change every single string instance of the name. You don't want it to be hard coded in that regard. You want to just be able to change a single variable at the top, and things are a lot easier. If you have 20 variables, you have to use 20 variables. You can't just not use them. So for example, it says above that there's a maximum of 20 cars in the race. So that means that they could be less than 20. But as I say, if you've got 20 variables, you have to use 20 variables. You can't just knock off a few in your code. It doesn't work like that. Whereas you could loop through an array, and you can loop through an array, you can write your code so that you're not setting a certain amount of data, you're just looping through the entire array basically. So it's much more flexible that way. So let's put some of what I'm saying actually into words, because it's a bit haphazard at the moment. So firstly, an array can group all items under one identifier, the identifier being the name you give the array, as opposed to 20 separate variables, which all need separate identifier names, which is a bit of a pain and is less readable. Having just a single line of code is obviously preferable to having 20 additional lines of code that all say pretty much the same thing. So each needs unique names or unique identifiers. We could also say what I was talking about in terms of having less than 20. So if there are less than 20 cars, then the 20 variables are still hard coded and need to be assigned some data. So probably just maybe null or 0, I don't know what this data is exactly, to be assigned some data. Otherwise you'll get an error because the variable is unassigned. It needs to have some value put into it before it can be used. Whereas an array is more flexible and can store fewer than 20 items. Even in some languages where you have to actually say how long the array is, you can still store less than what you've allocated. So you can store fewer than 20 items and use a single loop to go through them. I don't know how exactly you would deal with the 20 variables. Perhaps you would have to use a very long if statement in order to have the same effect as going through each of them. I'm not sure you could really loop them without changing them to some other data structure, which defeats the point. So that's it. So hopefully this is 4 marks, and we'll get our final mark for just saying that an array would be much more suitable. And we could just add in 2 more reasons very quickly. Probably wouldn't get any marks, but it's worth just to be sure. Much more suitable due to this flexibility and the improved readability. Okay, so I probably shouldn't have done it all in green because that's a bit garish, but there should be 5 distinct points there. And the company collects, stores and processes data about its customers. It collects their names and postal addresses, and they store this data in a CSV file, a comma separated value file, where they just separate each bit of data, each field with a comma. Very basic file with 1 record per line, so 1 record corresponding to 1 customer, and it contains over 5,000 records, and part of this is shown here. So postcode first, and then their name and their address. Okay, I want to send a newsletter only to customers whose postcode begins with PP. So yeah, so it's we've got 2 here, and we need to explain an improvement that can be made to the data from the file when used for this purpose for 3 marks. So basically you can see here they're not ordered. We've got 5,000 records, so that is an important bit of information. There's tons of records here. This might take a, not substantial, but it will take some amount of time to go through every single one and pick out only the ones which start with the double P. So it's better to sort them. So if this is their purpose, if they were always going to do it by the first two values of the postcode, they could just sort it in that order, so have these next to each other. So that's much more efficient than having to check every single item. What you could do, you could basically, if you just had a block that were all with this value, you could just search through it, get to it, and then once you reach some other one, just stop, instead of having to go through the whole document in order to pick out every single instance of this postcode. So records could be sorted by their postcodes, i.e. all P postcodes are in a block. This means not all records have to be searched in order to extract this information, because you know when you finish at the block, because you come on to a next one basically as the order changes. I'm not sure that makes sense, but anyway, so that's 3 points for 3 marks. The second part, before driving the cars, each customer fills in an information sheet. If under 16, we have to have it completed by a parent, and it's stored on the hard disk of the computer. And we're given an excerpt of this, and we have to identify 2 ethical issues of collecting this type of information. So we've got sort of basic stuff like the name, address, postcode, so just basic personal details, height, weight, which usually you maybe wouldn't want them to collect, but in this case, if you're driving a car, perhaps if there's an upper weight limit or upper height limit, minimum height limit, so on. And also medical information. So this is obviously important if you suffer from seizure. That seems kind of fair enough for them to ask. But we have ethnic origin here, which is maybe less... It's less clear why you need that information for driving cars around a racetrack. So perhaps this is less ethically sound. And obviously the nature of ethics is that they're kind of... There's no right or wrong answer, so... Yeah, so you could say that collecting, as it has no relevance to driving. There are some scenarios where collecting this kind of data is necessary, so maybe a government, or if you apply to university, you'll tell them your ethnic origin, and it's useful because it means the university can make sure they're not discriminating against a certain group as a percentage of the population and so on. So it is important, but not really for this purpose, although they might justify it. But again, this is all about ethics, so it's kind of up to you. The second one is less clear, to be honest. I mean, maybe you could say something about, I don't know, the email. Not everyone maybe has an email address. Maybe people wouldn't want to give their weight. Maybe you can say of the ethnic origins they give, you know, white is just the category, but then you have specifics for black and Asian. I mean, Asia's been limited to 4 countries here, so issues like that. Let's stick to this theme and say, generally speaking, not all ethnic origins are specified. I know it's quite a weak point, but it's a point and you'd get a mark for it. Specified. So it's a small range, which is maybe slightly unethical, although it's not going to be a huge deal. I don't think anyone would be too offended by that, but still, it could be an issue. And next, a slightly more standard question. Give a reason why it may be illegal for organisations to share their data with third parties, i.e. another company. So this might be for marketing. Maybe they'd sell this data to a marketing company and they would, spam them with loads of information. So so the issue is all about permission for data protection. So with no permission, I don't think you especially need to know this, but the law that covers this in the UK is the Data Protection Act. And one of the aspects is, well, it's mostly about permission, to be fair. So they can't do anything with your data without your permission. Question 10 is a 6 marker. So each car has a pedal to make it go forward. But yeah, the closer the pedal is to the floor, the faster the car goes. The further the pedal is from the floor, the slower the car goes. Each car has its speed limited to 15 kilometers per hour. And we're going to complete the flowchart over here. So a relatively complex flowchart, I suppose. It's all relative, of course. And let's just try and work out roughly what's going on here. So we've got, well, we need to start somewhere first of all. So this gap is going to be our start symbol. So that's just gets one out of the way, I suppose. You just start symbol. And it's kind of like that. It's meant to be more like curved, but anyway, get the gist. And so first of all, the variable speed set to 0. The old position is the height of the pedal off the floor. Okay. So you can see here we've got the condition that it said it's got to be less than 15 kilometers an hour. So it's checking if its speed is less than this, and if it is, then it will add something to it. It will increase it by 0.5, and it will go back and check whether the new position is greater than the old position, so whether the driver has actually put the pedal down or not. So if they haven't put it down, it goes back to the start. So this is a little bit confusing, but what's happening here is the driver is actually doing something. So they're actually pushing the pedal down onto the floor of the car in order to accelerate. So if the new position is greater than the old position, i.e. it's higher, that's the wrong colour to use, it's higher than the one previously, that means, so if this is the new position and this is the old position, then it's moving that way, i.e. you're trying to slow the car down, you're trying to accelerate less. So that makes sense why this is down here decreasing it by 0.5, whereas up here it's increasing it by 0.5. So this is going to be old position old position greater than new position, and it's going to be within a decision symbol that's not drawn very well. So let me try and explain this. So we've got the floor of the car, and we've got our pedal like this. This is the old position, and now the driver's put their foot down on the accelerator, and now it's a new position, so it's closer to the floor. So this is the new position. So therefore, the distance between the floor and the pedal are different. So the old is now bigger than the new position. And then we need to, so if that is true, we need to, so this is not good, but connect it up, and we need to go, so if it is, then this is going to be yes, because you want it to accelerate, i.e. you've made that change to accelerate more by putting the pedal down, and this is going to be no. Hopefully you draw it better than me. And this is, those are all the gaps. I think those are all the gaps needed. In fact, we've got a missing one here, so this is just going to connect here. So hopefully I explained that okay. I was obviously trying to figure that out myself, because it's a little bit complicated when you have gaps, but especially because it's lots of connections here. But if you understand the logic of what's going on, I think just for understanding that the larger the height, going to a smaller height means you're accelerating, and vice versa means you're decelerating, which is happening over here. That's all what this is doing. And also, because it's not super clear, and this is a loop by the way, so that's why you don't have a end symbol, because this is just for the generic process of speeding a car up. There's no end as in you stop at your house, because there's no details about that. This is just a continuous process that gets repeated, hence why it loops all the way back here. And this is just a stage where something's got to happen, which is why they have the same value. So there's got to be some kind of storage to store the old position, clearly. And remember that the decision box, the diamond, has got to have two outputs, either yes or no, true or false, basically, that's what it's representing. For part B, each car has direction indicators which are controlled by an indicator switch operated by the driver. It has two indicator lamps, one on the right and one on the left, and the switch has three positions. Middle position is the off position, the up position is to indicate a right turn, and the down position is to indicate a left turn. When the lamp is turned on, it flashes on and off in 0.5 second intervals until the switch is moved to the off position. And we need to actually do a flowchart ourselves for this for 6 marks, so that's going to be interesting with my drawing. Let's get the start symbol out of the way then. So as I say, it's meant to be a little more of a straight than curved, but anyway, it's clear what that does. So what we're doing, we need to first of all decision, so let's just say we're going to go straight into a decision block. So let's do, in fact let's probably write it first before drawing around it. So is the switch left, in fact my mistake, it's meant to be is the switch down, which corresponds to left or right, I'm not sure. So let's just check, is the switch down means that it indicates a left turn. So if this is yes, we need to do a left turn, which will just be a process box. So a process box is just a normal rectangle. Do a little arrow there and do an arrow here. So let's just go back and check what's happening. So when a lamp is turned on, it flashes on and off in 0.5 second intervals until the switch is moved off. Okay, so we turn it on, we wait 0.5 seconds, so again just another process, and then because it needs to flicker on and off, we turn the lamp off again. So another process box. And obviously this needs to repeat, that's the whole point. So we need a condition. So it's gonna flicker until the switch is turned off. Or more specifically, is switch in middle position. I never leave myself enough room to do the box, so I would recommend you do this in pencil yourselves first, or at least sketch it out in pencil, and use a ruler if you can. So if it is, we want to loop back to the start. And when I say back to the start, I mean back to here. Otherwise, we're gonna do something else. We need to do the other side of this equation first. So whether it's if it's no, instead, we need to check whether the switch is up. And I'm going to do the exact same process here. Okay, so this is a complete mess, to be honest, but it does the job, I suppose. So we need to actually wrap this up and say that, so if it's no, we can kind of connect this now. But these are two separate processes, hence we've got two separate boxes asking the same thing, basically. They're kind of self-contained. We need to go back to the start, and I've left myself in a bit of an issue here, so let's just go straight through this and loop it right back to the start, just to repeat this process, so it's a continuous process, which is why I don't have an end like before. So both of these are going to be no, and it's going to go all the way back to the start. And then this one's going to have a no, so it's got to something's going to happen when you do no. You've got to complete both options, and the game's just going to loop back because nothing's really happening. It's in the off position if both are no. So that way, this is no. Okay, so this is it. Very messy, like I say. Yes, not really much more you can add to it. There's only 4 symbols you're ever going to use, and if you don't have an end symbol, it's because you're looping back to the start. It's a process that's continually happening. It keeps checking basically for this. Otherwise the indicator wouldn't work. So 11 is the final question of the paper, and to start a race is a light sequence. So at the start only the red light is on, then it goes off and the first amber light goes on for a second, then that goes off and the second amber light goes on for 1 second, then it goes off and the green light shows to start the race. Now the program that controls this has 2 requirements. First of all, the race controller has to enter Y to start this countdown, and when a car makes a full start it breaks a light beam and the race is stopped. And it has 3 sub-programs that have been written that we're going to use. First of all, count grid breaks, which returns the number of cars breaking their light beams. Stop race resets all lights to their initial state and informs the controller that the race is stopped. And wait is suspends execution for 1 second. Okay, and we need to write an algorithm in pseudocode or in the language you're doing to control this sequence for 9 marks. So I should have really done this with a flowchart as well, but you should really take some time to actually plan this out, at the very least in your head, so you know what you're doing, or do it in pencil because you're bound to make changes as you go through it and spot mistakes and spot changes to the flow of execution. So basically you can write this in any way you want, but not as a flowchart. So firstly, this whole sequence, as we've been told, starts because the race controller has entered Y into his or her keyboard. So we need to have an input here. So let's just say input equals input from the keyboard, to input, just say enter Y to start. And it does say that only Y is going to be used to start the race. So we need a loop to make sure that only Y is actually going to be used. So we can say while our variable input does not equal Y, then, and this is my own pseudocode. You don't have to use Edexcel pseudocode. You can if you want to. As I said, it's in that booklet you get given, but you don't have to do it, and you could do it in your programming language or pseudo programming language. You could do like adapted Python, which is similar to this except with lowercase letters, but so on. Basically you can do roughly what you want as long as it resembles program code. So when the input is not Y, we loop and want more input, so we basically ask for it again. So we just say input again. You can see we're accessing this global variable. We haven't declared it as a local variable, so we're all good here, and we can end the loop at this stage. End while. So that's kind of our first issue out of the way. Once this has been completed, once input becomes Y, because the input has been put in however many times, it could be a million times, it could be your first try, we move on. So this is finished executing, so we can actually do the sequence now and program that. So let's go back and look at these subroutines again. So I have to enter, when a car makes a full start, it breaks a light beam, the race is stopped. So if a car has broken this light beam, so you've got the light beam, and if a car has broken it, I can't draw a car, but if it's broken it, then this sequence isn't going to start. So we need to use count grid breaks here, and we want this to be 0 basically. The goal is to have this as 0. If this is not 0, then we've got an issue and we've got to stop the race. So let's do a different colour, so it's not continuous. So to an if statement, if, I've completely forgotten the name of it, count grid breaks, just using that, equals 0, let's do equals to compare it, equals 0, then we can actually start the sequence. If a car has broken this already, then that's obviously, you're not going to start the race because they've already cheated. So we have the 4 lights, and we don't know exactly how that's going to be referenced. Let's assume it's going to be, red, amber 1, or 1 amp, no, it's convention to do the number after, so let's do amber 1, amber 2, then green. And let's do them, so you've got to be thinking about what kind of data type would be used to store these, and really it's going to be a Boolean value. They're either on or they're off, aren't they? They're not blinking like the indicators. It's going to be on or off, so true or false. So red starts first. Red is on just permanently unless the actual countdown starts. So let's do let's go red is true. Let's do it in capitals. In fact, so that's a mistake. As I said, you're going to make changes, which is why it's better to do it in pencil unless you plan it out very well. So in fact, this is going to be up above here. So let's sort this out. Because red is just on permanently, just to indicate that the race hasn't started yet. So it's actually going to, the first action in this is going to be to, let's indent it, is to go to red to be false, because red needs to go out basically, doesn't it? Because otherwise you're going to have red and amber on at the same time. So amber 1 I think is first, so that's what I mean. So I reread this, which is why I changed my mind, because only red light is on at the start and then the sequence starts, so it goes off and the first amber light goes on for 1 second, and that's what wait does. So perfect. Okay, so amber 1 becomes true, and we use for subroutine wait or subprogram wait to wait a second. So amber 1 is currently on, we've waited a second. So if someone does a false start here, that's an even worse car, then we need to check that again. So we need to check the light beams, the situation with the light beams, before actually putting amber 2 on. So let's do this as our if colour. So if count and proceed and put amber 2 on. First we've got to turn amber 1 off and put amber 2 on, and I imagine we wait again. Yeah, it goes off, goes on for 1 second. Okay, the next stage is to check again if there's been a false start, so we need to copy, let's just copy this to save time. Check this is done, and let's just indent it to make it more readable, even if we're going off the side a little bit. And the same or very similar process, we have to turn amber 2 off at this point, so amber 2 becomes false. It's very repetitive, which is a good thing I think in this context, because it means it's easier. Then green will go on at this point, and then what do we do here? So is that it, or does it it goes off and the green light goes on? So I guess that's just it, green light kind of stays on indefinitely. But we need to actually end this by saying, well, if it isn't 0, what do we do? We have to stop the race. I'm going to go on to the next page, so we're going to actually stop the race by calling this subroutine, which is fortunately not something we have to code, and this is a bit of a pain. So let's just end this if statement. I mean to do the same with the nested one, or the one at the next level. So end if, and we'll do the same thing here, making sure we line it up properly for the other one, because we can see we've got 2 ones nested. In fact, we've got a third one we need to do as well. So again, just very much repeated code. So this is just stop race, and the same thing again, so going 1 more across. So exactly the same process. We've got to make sure we have all execution paths covered by this. So try and keep your pseudocode consistent. If you are doing capital letters, keep doing capital letters for keywords. If you're doing an indentation, keep doing indentation. You don't want to confuse the examiner. But that's it, I believe, for this question. So a few stages. It's all about interpreting the information they give you. They give you a lot of information. It's often in bullet point form, which is really helpful. So for example here, you know that's going to be a few marks each, and it kind of sets out how it is. So it's 9 marks. Often people do a minute mark. Obviously this is a 2-hour paper and it's worth 80 marks, so that's not going to apply directly. You might want to give yourself maybe 20 minutes if you're really going to struggle with these. You can't control how difficult they're going to be. Some are quite challenging, some I'd really have to think about, others I could do quite easily. So this was quite an easy one, to be fair, although of course you may disagree. It's all individual, I suppose, but don't worry about it too much. It's only 9 marks. Well, 9 marks is quite a lot, to be fair, but it's not going to ruin your grade necessarily. If you ace the rest of the paper and get 0 marks on this question, you're going to be okay, so don't stress about it too much. So well done for getting this far. Like the video if it was helpful, and let me know if you have any questions, and thank you for watching.